Okay, so everyone is here.
Okay.
It's 10:30.
Where is...
All right, so I will open first, and I'll hand it to you.
Okay.
Selamat pagi semuanya. Good morning.
Selamat pagi, Bu.
Selamat pagi. Sudah datang semua ya, terutama kelas saya. Teman-teman mahasiswa S1 ini sebenarnya terbuka untuk mahasiswa yang lain. Saya tidak membuat iklan, itu saja. Jadi jika ingin share linknya ke teman-teman yang lain boleh, silahkan aja ya. Ini lecture-nya masih kurang lebih masih 1 jam, 1,5 jam mendatang. Okay, so good morning everyone. Good morning students. We meet again today. This is the last week actually, Ranjan, the last week for our students. Next week they will have a final exam.
Okay.
So the last week will be, the lecture will be delivered by my colleague here, Ranjan Jha. I actually shared your website to my students, so they probably check it out. I don't know whether students have already done it. So yeah, I forgot. I will give a short introduction about Dr. Ranjan Jha. So he has done a PhD in École Centrale de Nantes, right, with me, more or less. We were there about the same time. Then he continued for a PhD, for a postdoc to Montreal.
Yeah, Montreal.
Montreal, okay, in Canada. That's quite far away from here. And today I invited him to give a lecture about an hour. It's up to you, Ranjan, but I will give you a time slot about an hour and a half to deliver the lecture about parallel mechanisms, because that's our topic for our class. The last topic for our class is parallel manipulator. And at the end of the lecture, I will invite students to give questions.
Yeah, sure.
And of course, we will take advantage 15 minutes, 10 minutes question and answer. Right, Ranjan, I will give the time for you. You may give a short introduction about where are you from, where is the city, and so on.
Yeah, sure, Latika. Just 1 second, I'll share my screen.
Yes, I enable you to share the screen.
Okay. So you can, just 1 second. You can see my screen, right? I'll make it in present mode.
Yes.
Okay, so it's in presentation mode, right?
Yes, perfect.
Okay, hi, good morning, everyone. So thank you, Latifa, for the introduction. So I guess you all are studying robotics there, right? So I'll give you a little bit about the parallel mechanism, what we have learned. And I'll show you a little bit about our work, which we are doing here in my lab. So my lab is one of the industrial research lab specialized in instrumentation, actually. And we have different departments: biomedical, then optical engineering, then agri instrumentation. So basically our lab is focused on the instrumentation part. And so in biomedical instrumentation, I am doing a little bit work about the surgical robot. So I'll share also that with you. But I have put many videos just for the understanding what is robot. So I'll start my lecture. So there are, if you know that there are 3 important parts in robotics, right? So one is the electromechanical components, then the mathematics and physics. So what we learned about the kinematics, right? Kinematics and dynamics of any parallel mechanism, and then programming to run that particular robot, right? So these three mix up and give us a very good kind of mechanism or whatever we desired from the robot, right? So I'll start my lecture with this video. So this is a Tesla car. Tesla, everyone knows, right? So this is a Tesla car assembly line. So these are the robots which is installed there for working. So this is the serial mechanism. I think you have learned a bit about this robot, the kinematics and all. So this is just to give a glimpse that what is the industrial application of the manipulator, right? So why we go to why we install these kind of robots in the assembly line. So if you observe that, so the payload is very high, right? So you can say this, it's very difficult for human to manipulate this kind of payload, right? So that's why we need this kind of robot. And again, in the assembly line, the company's target is to have maximum number of to manufacture maximum number of product, right? So these robots help to maximize the accuracy and the productivity of the industry line. So you can see the manipulation here. So I'll not talk much about the serial mechanism, but we'll jump to the parallel one. Okay. So if we go a little bit mathematics, I have added few slides just to have the introduction about the mathematics behind these kind of robots. So so it's very important, right, to write or to write the programming for any robot. It's very important to mathematical model it, right? I think you have learned about this, how to model an object or any system to so that the robot can understand. So the main thing is to denote the point or any object on three-dimensional space. So these are few tools I think you have, because it's your last semester. I think you very well known. So I'll skip these parts. So these are the three motions, right, which gives us all different kind of motions. So one is the translation, rotation, and then we have hybrid kind of motions. And then there are transformation matrix. Suppose if a robot has to move one object from one point to another, so we use different kind of matrices or the mathematical formulations to model that, right? So don't worry about all this. So we'll directly jump to the parallel one. So I have put, okay, so this is, so I have added in the starting, before starting the parallel mechanism, I'll talk a little bit about the surgical robots. So you may have heard about the Da Vinci surgical system, right? So this is for the teleoperation, right? A surgeon can sit anywhere in the world and can operate a patient for any different kind of surgical procedure. So this is one kind of mechanism. So here also there is a parallel mechanism inside that, right? And it's a hybrid. It's a kind of serial plus parallel mechanism. So this is there, and now this is in many countries people are performing the surgery using this surgical device. So you can see the hand manipulation of the surgeon is very well it's very well transferred to the patient side card, right? So this is the current trend of the Vinci surgical system, what we have seen. But now, like I have put this one, so this is a snake-like robot. Now, before there were 4 incisions which we have to make to perform the surgery. Now with 1 incision, all the tools will come out. So there is only one trocar. From there, you can see this kind of snake-like robot which comes out and perform the surgery. So this is the current trend of the surgical robot. So with 1 incision, these 4 tools come out and perform the surgery, right? So these are the few things which we are doing in the development of the surgical robot. So here, few things, the handheld, and then so I'll show you one video just to understand. So these are few things which we have developed here in our lab with the tool also. So I'll show you one video just to know. Okay, this video is not working here. Okay, no problem. So from here I'll show you. So this is uh, the surgical tools which we have developed. So video is not working. Maybe I'll show you later that video. And so we have transferred the handheld motion to these like in the second number you can see, and we have developed one 4 number you can see here. So there is, while performing the surgery, so there is a tremor in the hand of the surgeon, right? So to remove, it's very important. Now you can imagine if he is doing surgery and his hand moves, so what will happen to the patient? So it's very important to filter out the tremor. So we have developed one device to filter that tremor of the surgeon handle. So I'll show you this video in the last. Okay. So we'll start with the parallel manipulator. I'll just give a glimpse that uh, there is a comparison between the parallel and a serial mechanism. So here you can see. So this is a parallel 6-axis parallel robot. So there are linear actuators, joints. So in the later slide, we'll take one parallel robot and we'll try to understand the mathematical model of that. Okay, so you can see here the motions of serial, and one can understand the difference between the two mechanisms. And then you can give a thought like in which application you can use what. Right. Now, let's try to understand like few terms before jumping to the parallel mechanism. So there is something called the constant equation, right? We'll see what is this. So there are two important terms, the workspace and the joint space. So with these constant equations, so for example, um, we represent in three-dimensional, if you take any object, so it has 6 degrees of three rotations. So the set of all the possible values of these variables we called as a workspace, right? And then joint space, you take the actuator. If you are taking the linear actuator, then you can denote as rho, or if you take a rotational, like a simple motor, you can take the angle of that particular robot. So if you plot all the points of that actuator, we called as a joint space, right? For a given pose variable, right, for a given particular value in the workspace, when we calculate the articular variable or the joint variable, we called that as an inverse kinematic problem. I think you know now these terms. Now, when we, so in the later example, we'll see while solving the inverse kinematics, it will not give the one solution. It will give the different solution because of the algebraic equations, right? So we called that number of solutions as the working mode of that particular robot. Similarly, for a given value of the joint, like the given value of the motor rotation or the linear actuator, when we compute the workspace, that is a point in three-dimensional space, we called that as a direct kinematic problem, and the number of solution we called as the assembly mode. So these working modes and assembly modes we'll understand with an example, right? So there is something singularities, we'll see also that one. So this is again one video for the parallel mechanism. So before start, let's have a feeling of this parallel robot. So this is for making the pizza, right? So you can see the different application of that, the manipulators, right? The robots. So here, so this is one kind of delta robot which is used to make the pizza. So you can think n number of application for different mechanism. So this is one of that. So the simple definition of the parallel mechanism is if you have more than one link connected with the end effector, we call that mechanism as a parallel mechanism, right? When you have the closed loop. Okay, so we'll just 1 second. Okay. So let's start with a delta robot. We'll try to understand. So now suppose take three any linear actuators. Just take random three linear actuators and think about how we can join these actuators in three-dimensional space. So based on that, so we have formulated four different kind of uh, delta-like architecture. So for example, let's suppose when these actuators are perpendicular to each other. So just put these actuators on each axis like x, y, z. So the mechanism we called as a orthoglide. So when two are parallel, we keep two parallel and one perpendicular to each other. We called as a hybrid glide. And when all three are parallel, we called as a triaglide. And when they are in different plane, we called as a Uranus X. Right. So let's start with hybrid glide. So hybrid is when we are keeping two actuators. So here let's okay. So here you see we are keeping this two actuators parallel and one is perpendicular, right? So this is the end effector. For example, let's suppose we want to paint a surface, right? So we'll fix a brush here at this point P, right? Now we want to model that. We want to make the kinematic model of this particular architecture. So let's start. So we take, if you consider this point A1, A3 and A2. Let me show you the motion of this mechanism first. So see, this is making a circle, right? So if you consider this point A1, A2 and A3, so these are the 3 points which is fixed, right? And B1, B2, B3 is connected with the end effector, which is the moving point. Now, how to find the kinematic equations? So if you see this point B1, so if you know the point B1 and this P, you know XYZ, right? So if you, for example, let's take these values of the actuator. This is the linear actuator, right? Let's suppose this is a row 1, right? This is a row 2 and this is row 3. So this is nothing but the value of the linear actuator. Or you can take R1, R2, R3. Now, if you see this point B, these are on the x-axis, right? So if you, for example, sorry for my drawing. So this is x-axis, right? And this is y-axis. So we are keeping two actuators here, right? So these are the two actuators. So suppose this is fixed, and we want to calculate these points. So this is B1 and B2. So, and this distance is rho 1, right? So our B1 point will be what? It will be one point we can take as 1, comma, rho 1, comma 0 because z is 0, right? Another point we can take as, so this point will be minus 1, rho 1, and this point we can take as 1, comma, rho 2, right? So we have the, or you can take this as rho 1, this as rho 2. So now we know these 2 points B1, B2, and we know this P as X, Y, Z. So the distance between the 2 points is what? X1 minus X2 whole square plus Y1 minus Y2 whole square plus Z1 minus Z2 whole square. Sorry, and under the root, right? So with this, with the help of these constant equations, we'll arrive with these three equations. So this is nothing but distance between point B1P. So B1P equals to L gives us the constant equation. So when we solve, now if you see here, X, Y and Z are the pose variables, right? So in the last slide, when you plot this X, Y, Z, we called that as a workspace. And then you have row 1, row 2 and row 3. When we plot this, we called as a joint space, right? So X, Y, Z is the pose variable, row 1, row 2, row 3 is the joint variable. When we want to calculate X, Y, Z, when the row 1, row 2, row 3 is given, we called that as a direct kinematics. And when we want to compute row 1, row 2, row 3. When x, y, z is known, we call it as a inverse kinematics. So if you see this three equation, now for example, if you know x, y, z value, this point, this is a circle, right? So we know set of all the points. So when we substitute here these points in x, y, z, we can very simply by solving these three, because now there are three variables, right? Row 1, row 2, row 3. So by solving these three, row 1, row 2, row 3, we can get the value of these actuators, right? How much we need to move this actuator to get a circular trajectory. So this is with the help of these equations, we can able to calculate that. Right, now let's check this mechanism. So this is triaglide, right? So all the three are in the all the three are parallel and are in the same plane, right? So now what is your what you can think of? You can visualize these different mechanisms, different delta robots, and you can think of different application where you can fit these kind of mechanism, right? So similar way, you make a xyz like this trajectory, the axis, and then try to put these actuators here, try to find the point b1 b2, and you can able to write these equations. It's very simple, right? Sorry. So you can see, to make a circular trajectory here, you can see the motion of this mechanism. Now we will go to the Uranus X. So this is 3 perpendicular but on the different plane. So this is very familiar, right? Many when you see the 3D printing application, many mechanism you will find, like the most of the mechanism, the parallel mechanism for 3D printing will be like this only. So 2 in the same plane and 1 in different plane. So you can again write the b1, b2, b3, and with the help of the b1p equals to L, you can able to write these 3 equations. So the motion is something like this, right? So this is we called as a Uranus X, and the application is in the 3D printing, or you can think any different application also. So now let's go to the orthoglide. So this is this very simple one. So this is one of the example which we had in at France École Centrale de Nantes, this manipulator. So we have seen that when you place the actuators on the 3 axes, right, x, y, and z, you can get this mechanism. So how to model that? So again, the principle is again the same. You first find the point b1, b2, b3. So you know this one is on x, y, and z axis. So the point may be row 1, comma 0, comma 0, and then other point will be 0, row 2, comma 0, and the third point will be 0, comma 0, comma row 3, right? When we find 3 points, then we will calculate the equation like this. So this is very simple equation. So here this is the constant equation. Again, with the help of b1 p equals to L, we have found this equation, right? So the 2 points are row 1, 0, 0, 0, row 2, 0, and 0, 0, row 3, right? Now with the help of these equations, we can able to write the inverse kinematics and direct kinematic equations. Now let's take an example to understand this. So with the help of these 3 constant equations, so these 3 are the constant equation, right? What we got in the last slide. So when you find the x, y, and z from this equation, you will get these equations. Now you can with hand also you can solve this, but you can use any mathematical tool like Maple or MATLAB to compute these equations. It's not very difficult to find these equations. Similarly, the inverse kinematics, the inverse is very simple. Now, when you compare the serial mechanism with the parallel mechanism, so one can observe that here it's very easy to find the inverse kinematics for the parallel mechanism. So this is one of the advantages of the parallel mechanism, that you can able to write the inverse kinematic model from the constant equation very easily, right? You can see from here. So it's very simple, right? L square minus Z square minus Y square, then under the root, then plus and minus X. So this is rho 1, rho 2, and rho 3, the inverse kinematics. Now, so we have seen about the workspace and the joint space, right? So here, if you see, we talked about the pose variables. So this X, Y, Z here is the pose variable, right? We called as a, to know the position, we called as a pose variable, and rho 1, rho 2, rho 3 is the joint variable, right? So when we plot this X, Y, Z, we'll get a certain kind of region. So this is the workspace of the that particular orthoglide mechanism. Now it's very important. For example, if you are making a robot for any industry, right? So the user should know about this workspace. So he should know that where their robot will travel. So this kind of study is very important to perform before delivering any robot, right? So there are different colored regions are there here. So the meaning of this regions are, when you take this yellow region, so we have computed these surfaces as the different number of solutions for the inverse kinematic problem, right? So suppose if you take any, this is XYZ, right? So if you take any point from this workspace and if you calculate the inverse kinematic solution, you'll get the one solution, right? And so the inverse kinematic solution means, so if you see this equation rho 1, rho 2, rho 3, so for any particular values of x, y, and z, when you calculate rho 1, rho 2, rho 3, you'll get certain number of solutions, right? And you see there are plus and minus. So there are maximum 8 different possibilities you can get, maximum number of solution you can get from these equations. So this green region is, so if you take a point xyz from this green region, you will get the 8 inverse kinematic solution. Similarly, this R1, R2, R3 is nothing but rho 1, rho 2, rho 3. So when you plot all the possible actuator values, like, right? So when you take any actuator, linear actuator, so it has value, right? So when you plot these value, you will get this surface. And if you take any point rho 1, rho 2, rho 3 from this surface, you will get a 2 number of direct kinematic problem. That is, when you substitute this rho 1, rho 2, rho 3 here, and when you solve x, y, z, you will get 2 number of solutions for that particular equation, right? So the meaning of what is the meaning of this work, like the assembly mode and the working mode? Suppose let's understand with the from here. So if you take, so first we'll talk about the inverse kinematic. So for particular values of rho 1, rho 2, rho 3, for example, let's say rho 1 is 1, comma rho 2 is 2, and this is 3. So 1, 2, 3, for 1, 2, 3 value, you can get different points, right? 8 number of solution means you can get point here, 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 here. So your end effector can be anywhere among the 8 points. So this is the meaning of, the physical meaning of the number of solutions. Similarly, in the inverse way, for this particular point, you may have different configuration of the actuators. Right? So it is very important to know about these values. So once we know about the workspace and the joint space, we go for the singularities. Now, what is this singularities is? Sorry. So now, for example, when we compute, again, let's take this. So here, now we know these 3 constant equations, right? So these 3 are the kinematic equations of this particular robot. Now still we are talking about only the position, but this is a moving structure, right? So there is some dynamics also. Now, when you map this actuator, the velocity of this actuator with the velocity of this end effector. So when you map between x dot, that is the velocity of this end effector, to rho dot, that is the velocity of the actuator, right? Or the double derivative, that is when you taking again one more differential, that is you are computing the acceleration. So that is double dot. So you are computing these values from here only, right? So let's see this. So you know this x, y, z, right? So when you take the differential x dot, y dot, and z dot, so we called that as a Jacobian, the matrix which we use to map between the velocities of the end effector to the joint variables, right? Now these are the mathematical matrices, right? So when the determinant of that matrix becomes zero, it's very difficult to map those velocities, right? So that particular point we called as a singularities. And this it's very important to know this singularities, because in parallel mechanism you can find the singularities inside the workspace also. So physical meaning of this singularity is, at that particular point when your manipulator crosses the singularity, the stiffness of the manipulator will lose, right? So for example, if your manipulator is moving, it will fall down, right? So it's very important to know that particular singularities inside the workspace, right? So I'll not go much mathematical. So for that particular robot, orthoglide, we have computed. So this is the singularity surface which is inside the round one. So for orthoglide, it's like a sphere, right? So inside sphere, you have these kind of surfaces. So this is not the safe zone for any robot, right? So we should give this value to the user that your robot should not move on these points, right? So whenever you want to make a trajectory, for example, if your robot want to move from this point to this point, it should not move like this. So first you should ensure that it should not go pass through the singularity. So this is the second step what we are doing in uh, the trajectory planning. So we will see that also. So here, if just for the analysis for different for the orthoglide, so if you see the singularity in the workspace, so you can see this surface and this surface. So we'll see again this. Okay, so this is the video of so you see. Okay, so now in that point, so when it fall down, so it passes through the singularity. So when it passes through the singularity, you can see that here. Just 1 second. Okay, so here you can see. So when it passes through the singularity, it loses the stiffness and it falls down, right? So that's why it's very important to know about the singular points in your workspace. Now in the trajectory, what we do, so these are the parametric equations, right? What we use to write. So I'll give you a little bit about what is the parametric equation, because sometimes you will find it useful. So what we do, we write, let's suppose you have 2 points, right? A and B. So this is point A, this is point B. So what we are learning now about the parametric equations. So what is this parametric equation? For example, let's suppose if you want your robot should write your name, the initial of your name. For example, if your robot want to write something like this R, right? How a robot know about this? How to write the equation for this particular trajectory so that your robot will write the R. So we are learning now this one. So what we do, we make a line, we take a points. For example, let's take these 2 points here, A and B. And then we define the equation. Now let's suppose this point is x1, y1, and this point is x2, y2. X2 and y2. right? Now we want to have a mathematical equation which will give at t equals to 0. So when the time starts, right, it should be at point A, and when t equals to 1, so when the time finish, it should reach at point B, and it should cover all the points between point A and B. So how to write that equation? So what we will do, we'll write x equals to x1, right, into 1 minus t plus x2, right? Similarly, y equals to y1 1 minus t and then plus y2, right? So now if you observe here, so take t equals to 0, right? So at t equals to 0, when you substitute here, what you will get? So this is x2 into t and this is y2 into t. So when you substitute t equals to 0, what you will get? X equals to x1, y equals to y1. So this point, right? When you substitute t equals to 1, you will get x2, y2. So this point. And when you substitute t equals to point 1, point 2, point 3 like this, you will get set of all the points on the line A and B, right? So this is what we called as a parametric equations. So this Hertz trajectory or this spiral trajectory we are getting with the help of the parametric equations. So once we write these parametric equations, we plot this equation in with the workspace and we'll see whether it is inside the workspace or not. So you can see this trajectory. Just 1 second. Sorry, yeah. So now, so we verify this trajectory. When it is inside the workspace, we simulate, and then the next part is we do the trajectory planning. So there are two terms when you read the paper or research paper. One is the path planning. So when we write these set of equations, so these equations are the path, right? We didn't give the information about the velocity or the inertia here. So when we add about the velocities and different control modalities, we called that as a trajectory planning. So this is also very important because again you should know about the payload capacity and everything about your robot, right? So how much velocity and everything you get. So all these study we do in the trajectory planning. So now you see this is the singular surface. So we should ensure that these trajectories should not cross this particular singular surfaces, right? Okay, so this is all about like how we start modeling and then what we study in the parallel mechanism to understand that. So now this is again our last video. This is again, we called that as a Geminoid, right? So this is again a new branch of robotics, like new kind of robotics. So these are the mimic of human beings. So you may have heard about the Sophia, right? Sophia robot. So we called that as a not humanoid, the Geminoids. And you can see here. So these are with their original ones. So this is again one new application area which comes under the social robotics. And again, you can think n number of different application of these robots. So of course, this robot we don't require here in the developing nation where the population is very much high. But again, this is very much required where there is a less population or the skilled laborers. Right? You can program these kind of robots to interact with other people. Okay. Thank you. Thank you very much. If you have any queries, then we can discuss now.
Hello, can you hear me?
Yeah, Latifa.
Okay, my audio doesn't work suddenly. Okay, do you have any questions from the students?
Me?
Anyone? So yeah, who is it?
It's Farhan.
Yeah, please, Farhan.
Hello, Mr. Ranjan. I want to ask about the trajectory planning.
Yeah.
You mentioned that we need to consider the torque control and how do we decide the torque that needs when certain part is a bit hard to obtain, like the hard shape from before. In the curve or the sharp edge is hard to for the robot to move, and then how the torque control is designed.
Yeah. Okay. So what we study in that trajectory planning is, so it's a very good question. So it's very important also to know. So I'll explain you. Just 1 second. So here. So now, for example, let's suppose we want our robot should write like this C, right? C we can write like this also and like this also. So you have sharp edges and you can, like, if you want to make as a curve like more realistic C, you should be able to move on those curves. Now when we write, when we take a simple parametric equations, for example, let's say we take this simple equations, or when we talk about x equals to x into 1 minus t and x to t. So when you take a velocity of that, so when you derive it with respect to time, so what you will get? You will get x dot equals to constant, right? And when you derive double dot, you will get acceleration as 0. So with that equation, driving a car. Now suppose a turn comes, you slow down your car, right? You won't go at 100 on the curve also. So that's why what you should have, you should have a variable velocity which should change on these curves. And again, to have very good motion, if you don't want to have jerk, you should have the acceleration also in terms of variables where you can control the variable. So what we do, we substitute this t as something called t cube, the third order, or something like the standard one. What we take c1 t cube plus c2 t square. So this is a standard third order equation, right? Similarly, c3t plus c naught. And with the help of those boundary conditions, like we calculate for t equals to 1, we compute this c1, c2, c3, c4 for our mechanism or for particular trajectory. And now here you can see that when you take the velocity, what you will get? 2t square, right? Again, it will be a variable in terms of time t. And if you take the acceleration, again, it will be what? 4t. So it depends upon the t. So at this particular curve, as your velocity is again time variable, it will be slow down. So what methodology we are using? We are substituting these equations with this higher order equation. So suppose if you want to have more fine motions, what you will do? You will again increase. You will take t on the fifth order, t power 5. But again, what you have to do? You have to compute this particular variable, this particular constant, c1, c2, c3. So this is a trade-off between like how much order you can go. More order you can go, your computational cost will increase, but your accuracy again will increase, and your trajectory will be smooth. So this is the thing, depends upon the application where we are taking the third order or the fifth order. We never take the simple parametric equations because the velocity is 0 and your robot can move. So what we are doing in trajectory planning, we make a chart like this. So this is x, graph of x, then we plot x dot. So this is the velocity graph and then acceleration graph. So in this graph, we see if there is sudden change is there or not. If there is a sudden change, that means it will harm your robot, right? So we always see this should be smooth, your acceleration should be smooth, or there should be a constant value, and your trajectory can be anything you can able to move. So this is about the trajectory planning what we do.
Okay, thank you Ranjan. Farhan, masih ada pertanyaan?
Sudah cukup, Bu. Terima kasih. Thank you, Mr. Rajan, for your answer.
Yeah, thank you.
Yeah, it's trajectory generations. I didn't teach about this. It's a bit advanced. usually I give this for a specific project.
Mm-hmm.
But nice explanation for this. Just to add a bit questions from previous student. So you give boundary condition, right?
Yeah.
The curvature.
Mm-hmm.
Okay.
So what we do, for example, if we want to write this particular c, right? So we write our initial velocity or the initial position x we know. Now x dot, we are putting x dot here, that in the curve it should be 20, for example, 20. It should go to 20. So in the equation we substitute 20, and with different boundary conditions we'll calculate this c1, c2, c3. And when you substitute this c1, c2, c3, at this particular point you will always get the 20, the speed. So you can set your speed on different curves.
All right. I'm just curious whether for mobile robot, does it apply the same thing, the same method of trajectory generation?
No. So for the mobile robots, actually for the aerial vehicles or any different things, so again the base is again the same. We are taking the higher order like the equations, but we are taking different algorithms because it's very difficult to compute these values in the real time. So this is basically for the milling type of operations. where you offline compute the trajectory, satisfy it, and then you reproduce it. But we are using different advanced algorithms for the real-time one. But again, for those algorithm, the base is again the same. We are taking the higher order, but the optimized one, where your computational time is less.
Okay, but it's still third order, fifth
Yes.
order. Okay. All right, it's clear. Is there any other questions? I have questions about those hybrid glide, orthoglide, urbanist X. What are the drawbacks and advantages? From what I've seen, they can follow the same algorithm
Space inside that. So you will always go for this URNSX. You can't achieve with this kind of manipulation like this one. So these have different workspace. After seeing the workspace, you can very easily find like which application you can able to select the triglide or hybrid glide or the orthoglide.
All right, so it depends on the workspace size.
Yeah.
How about the orthoglide? Orthoglide will be because all the three axes are perpendicular.
Yeah, so the orthoglide workspace, we have seen it's a sphere, right? So if you want to have like the spherical workspace, so you can go for the orthoglide. So the workspace is something like this, right? This sphere, where it goes. So again, we have to check for the two things. Not one, we have to check for the singularity also. So how much efficient workspace you need, in which directions. So this, where it goes. Yeah. So this is like a sphere for the orthoglide.
So this workspace you generated, so actually this workspace is bounded by the singularity or by the join limit?
It's both. Actually, this is the simple one which I have put, but we have computed for the, we are adding the joint limits also and the singularity also. So both computations here, but I didn't put here, but I can share the results with you. So we have computed, so it's at last what we have to put the joint limits also and the singularity also to give the like the better information of the workspace.
You made this in Maple?
Yeah, in the Maple.
Yeah. Nice one. All right. Is there any other questions from students? One more question. I'm asking more technical.
Yeah.
Your surface, the previous one, in your previous slide, maybe about join space or workspace. I forgot.
Which one? With the trajectory or the singularity?
This one. Yeah. So this is a surface of a parallel singularity?
Yeah, this is the surface of the parallel singularity.
For orthoglide?
Yeah, this is for the orthoglide.
Okay.
If you see this image, so you have like the projections. So this is a parallel singularity projection in the workspace. And again, the projection in the joint space.
Mm-hmm. You give a joint limit for this?
Yeah, for this we have given the joint limit.
Okay.
And this, if you see, so this is the serial singularities in the workspace. So serial singularities is always on the border, right? So you can see these three actuators. You have three different cylindrical rings. And this is the serial singularity in the joints, on the joint space, the projection on the joint space.
Yeah, but the serial singularity, it seems that it is inside the workspace, right? Not in the boundary.
It's in the boundary. So you see, because we didn't put the joint limit, so you see the big length of the cylinder. So if you cut here, so you can see.
Okay,
so all are on the boundaries.
Oh, those are the boundary. Okay.
Yeah.
So you mean this? Yeah, you didn't give the scale, so that's probably. So the upper workspace is inside this cylinder.
Yeah.
Okay. So because you give the joint limit, I'm asking the one at the Cartesian space, the parallel singularity. If you don't give the joint limit, what will happen? You will have a infinite surface.
Yes. So if you don't give, then for example, for this orthoglide, it's simple. So it's not much difference if you give the joint limits. But for different kind of manipulators, you will have very large work. Means with the help of this joint limits, what we are cutting those surfaces. So again, the equation will be the same only for that particular surface.
Okay. Thank you, Ranjan. Is there any other questions? I think it's enough. It's very clear. And what you have presented is really what we learned in the class. It's all about singularity. I've just finished last week with I'm using a website from Ilian Bonev, Paralemic. There is practical works there. So I use that for my students for the 3 RRR parallel manipulators. Yep, I've just finished about singularity, parallel singularity 2 weeks ago. And today's lecture is very useful for them to clearly understand. And once again, thank you very much for your time, Ranjan.
Yeah, thank you. It's pleasure.
And students, don't forget to make a resume. I open the submission from 11 up to 3 p.m. Don't forget to submit your resume today. Right, and we'll meet again for students next week in the final exam. The topic will be only about parallel manipulators from the week 9, if I'm not mistaken, from the week 9 up to week 15 today. And the exam will be offline, but bring your laptop because all the questions, it will be multiple choices online in your system. So don't forget bring your laptop, and we'll have an exam next week on Tuesday morning at the same time at 10 a.m. Okay, I will close today's lecture. Thanks for students for coming. Don't forget your exam next week, and goodbye, everyone.
Okay, goodbye.
Ranjan, just let me. You may, student, you may leave today's meeting, and we'll meet again next week.